Alright, so now that we've talked a little bit about how we can go from a Lewis structure to a three-dimensional shape, we're going to apply what we learned in Chapter 9, talking about the dipole of each bond, and how that dipole now relates to molecules overall, rather than talking about individual bonds. So let's take a look and refresh ourselves what a dipole really means. For a molecule like HCl, this is what the electron density around that molecule looks like. Remember that this large region of electron density on the right means that the electrons are around that atom more often. Because of that, this side of the atom has a partial negative charge, which we signified with a delta minus. And the hydrogen side had less electrons, which means that it felt a little bit of a positive charge, and so we called that delta plus. And so that difference between delta plus and delta minus showed us that that bond is in fact polar. Now when we draw a bond dipole, we're going to draw it from the positive side to the negative side, and we add a cross at the base of that vector. That cross tells us which end is positive, right? So we have our little positive here on the hydrogen side and our negative on the chlorine side. Let's apply that to molecules. And so, if we look at NH3, nitrogen, more electronegative than hydrogen. Right? That's how we choose which end's going to have that partial negative. Nitrogen has that partial negative. All these hydrogens have partial positives. And so we draw the three bond dipoles going from hydrogen to nitrogen. Now there is dipole as well for the nitrogen to the lone pair. Right? Lone pairs are obviously more negative since they are just electrons than the nitrogen atom is. If we think about the shape of this ammonia molecule, it's got 4 electron groups with 3 atoms bonded to it and 1 lone pair. If you remember, that's trigonal, pyramidal, and what that means is that as those 3 hydrogen-nitrogen bonds are all pointing up toward the nitrogen a little bit, and then because that dipole from the nitrogen to the lone pair is also up, overall all those dipoles are pointing from the bottom to the top. And so our overall dipole, which is shown in green here above, goes from bottom to top. Now, I'm going to sort of overlay it on the molecule itself because really it would look something like this, right? This bottom with all 3 of these hydrogens is really where the partial plus is. And this side up here with the lone pair is where the partial minus is for the overall molecule. This heat map for the electron shows that. Again, most of the electron density is up here at the top. That's where the partial negative is. And so this part down here is electron poor. There's not a lot of electrons. That makes it a partial plus. Now, if we have a compound, I'm going to use carbon tetrachloride as an example. Carbon tetrachloride has a very similar structure to ammonia. Right? We just replace we replace that lone pair with a chloride. And so there is carbon tetrachloride. Now between these two, carbon and chlorine, which of those is more electronegative? Well, it turns out that it's chlorine. And so our bond dipoles go from the carbon to the chlorine. Carbon to chlorine, carbon to chlorine, carbon to chlorine. With this, it's kind of hard to tell exactly how it balances out, but I'm going to give you a shortcut. Because there are no lone pairs on this molecule, even though each of the individual bonds is polar, overall the molecule is nonpolar. Let me say that again. We have no lone pairs. Right? We do have polar bonds. And I'm going to say that all bonds are equivalent. Right? That just means that we have all CCl bonds. We don't have 3 CCl bonds and 1 CH bond. Okay? If all of these things are true, then overall, it's non-polar. Right? Overall, it's non-polar. The reason for that comes from the VSEPR theory that we talked about in the last video, where the geometry of those electron groups spreading out as much as possible across that sphere so they don't interact with one another. Based on that geometry, all of the vectors that go along those bonds also will cancel each other out. Okay? And so anytime you have a molecule where all the bonds are equivalent, so they're all CCl, they're all BF, or they're all whatever, then as long as they have no lone pairs, it's going to be a non-polar molecule. Okay? And remember our discussion of electronegativity from Chapter 9, all CH bonds are non-polar. So anytime we have a CH bond, we think about it as being non-polar. Even though there's a slight electronegativity difference between carbon and hydrogen, we negate that and we think about that as being a non-polar bond. Okay. So let's do some examples. BrCl, let's write this out. Each of those has 7, so we should have 14 electrons. We've got 2, 4, 6, 8, 10, 12, 14. Now between bromine and chlorine, which of those is more electronegative? Remember, fluorine is most electronegative, and chlorine is closer to fluorine, and so we do end up having a dipole moment there, a bond dipole. And so the answer here is yes. Right? And I've drawn it there in red. BF3, trigonal planar. We've got B. That tells us that it's trigonal planar. So that's how I'm going to draw it. I don't need any wedges and dashes because it's all flat. I should have 24 electrons, 3 from the boron and 21 from the 3 fluorines. So I don't know if all of those lone pairs showed up, but there we go. Now, for each of these, now fluorine's our most electronegative element, so all of these bond dipoles will go from the boron to the fluorine. Now I'm going to draw these in different colors, and you'll see why in a minute, but they're all equivalent. It's all a BF bond, right? Okay, and there we go. Now, for those of you that like vector addition, let's do this the mathy way, the physicsy way, right? There's my red vector. I'm going to add to that vector addition. We do tail to head, and so the tail of one vector goes at the head of the last vector. And if I add all of these vectors together, I end up back at my starting point. If I ever end up back at the starting point, that means that overall there's no net vector. And so boron trifluoride does not have a dipole moment. From our previous slide, it satisfies all of those rules. It has no lone pairs. The bonds are polar, but all the bonds are equivalent, and so they all cancel each other out. Right? And so BF3 does not have a dipole moment. If we take a look now at CH2Cl2, I'm going to put my chlorines here in the plane, and my hydrogens out of the plane. Between the two atoms, chlorine's more electronegative, and so we've got our bond dipoles for chlorine like that. Remember what I just mentioned about carbon and hydrogen. There's really no difference in electronegativity there that's worth mentioning. And so we don't draw any bond dipoles for those. We say that that's a non-polar bond. And so we have our two polar bonds here. Do those two cancel each other out? No. And so if we were to draw in an overall bond, right, it would look something like this. And so yes, there is a dipole moment for dichloromethane, this molecule. Okay. All right, the last topic that we're going to talk about in Chapter 10 is hybridization. And hybridization takes a look at where do these shapes come from. Right? It's one of the tools, one of the models that helps describe where these shapes come from. And so, for a hybridization, we mix two or more atomic orbitals to form new hybrid orbitals. Well, what does that really mean? Since it has to be two or more atomic orbitals, we're going to start with carbon. And so, for carbon, we would take the valence shell for carbon. So carbon is 1s2, 2s2, 2p2. If we were to draw that out, we have 1s, 2s, and 2p. Hope you remember your chapter 7 stuff. They start at the bottom, 2 electrons in each orbital, except if we have orbitals of equal energy, we spread out those electrons with their spins facing in the same direction first. So here's carbon. Now this has not been hybridized. The hybridization process says that we're going to take this and we are going to sort of blend these valence orbitals together. Right? So to blend together these valence orbitals so that we get some new hybrid orbitals. Okay? A few rules about hybridization. We mix non-equivalent orbitals. And so what that means is that we can't use two S's or two P's. We have to mix S and P, for example, like we're doing here with carbon. Right? Hybrid orbitals have new shapes. And that helps explain some of the molecular geometries that we've seen. The number of hybrid orbitals that we make has to equal the number of atomic orbitals that we started with. And so here we start with one 2s orbital and three 2p orbitals, and we're going to hybridize those into a total of 4 sp3 orbitals. This is technically 2 sp3 orbitals. Now we call it sp3 because we used one s orbital and 3 p orbitals, and that's where this term sp3 comes from. Now notice that they're sort of all together here. The 2s and the 2p total have 4 electrons. Now this 2 sp3 has 4 spaces. And so our 4 electrons get spread out over those 4 hybrid orbitals. Okay? This gives carbon the opportunity to bond with 4 different atoms. Let's say it's a hydrogen, right? To form CH4. Each hydrogen brings in 1 electron, and so that hydrogen can then sort of pair up with one of those electrons in a hybrid orbital from carbon, and we end up with CH4. So how do we get these new shapes? Well, if we look here, we have a 2s, a 2p along the x-axis, a 2p along the y-axis, and a 2p along the z-axis. Mathematically, when we add all these together, what ends up happening is that we get 4 different sp3 orbitals that end up pointing to the directions of the tetrahedron, right? To these vertices of a tetrahedron. And so that's why molecules that have 4 atoms bonded to a central atom all have a tetrahedral shape. One thing I want to point out is that this point here is the center atom. So that would be carbon in our CH4 case, right? And then you'd have a hydrogen at each corner that's bonding with that carbon. Okay. So here's what that overlap looks like. Hydrogen only has a 1s orbital. It can't hybridize. So this would be a hybrid orbital, sp3, interacting with an s orbital from hydrogen. What we're getting is we're getting overlap of those two orbitals, right? This overlap is our covalent bond. What if we don't need to hybridize all of those orbitals? Here, we have sp orbitals, where we just have one s orbital and one p orbital. Now we start with two atomic orbitals, we better get two hybrid orbitals. It turns out we get two sp orbitals, right? Sp because we've only used one s and one p. So the superscript there doesn't tell us really about the number of electrons in that orbital. It tells us about the number of atomic orbitals that were used to make those hybrid orbitals. And so here you can see that the beryllium, the two sp orbitals in beryllium, so here's one sp orbital here. I'm going to outline it in green. They're not really showing the other tail of it, right? There's one. And then the other sp orbital in beryllium is here. All right, looks something like that. Overlapping with the atomic orbitals in chlorine. For all molecules that have sp hybridization on their central atom, we end up with a linear molecular geometry. Just like with sp3, we ended up with tetrahedral. With sp, we end up with linear. If you print it out, or if you're following along on the sheet that's on Moodle, there is a column there for hybridization. And so all those with one central atom and two electron groups are going to be sp hybridized. The ones with one central atom and four electron groups, those are all sp3. That's what we've seen so far. And then here's sp2, trigonal planar. Right? You can see here that these are all trigonal planar. These are all sp2 hybridized. Right? We have one s and two p's. So in those instances where we do that, and so remember what we talked about with the expanded octet, those extra electrons have to go in the unused d orbitals. So how do we determine hybridization? Well, first and foremost, we need the Lewis structure. You'll notice that this is a continuing theme, and this will be a big part of organic chemistry. Right? Knowing the structure of a molecule is really a key component of chemistry and moving forward. So draw the correct Lewis structure, and then just like we couldn't determine the geometry of the whole molecule, we have to determine the geometry for each central atom. Similarly here, we're going to determine the hybridization of each central atom. And so for each atom, we need to determine the number of bonds and lone pairs. Right? I'm going to lump this, bonds and lone pairs, I'm going to lump this into electron groups. And so, number of electron groups. Here, I'm going to make a little table. The hybridization. And then I'm going to tie it back to our electronic geometry. Okay. Now remember, this is not necessarily our molecular geometry, but our electronic geometry. And so if we have two electron groups, we just saw that with sp hybridization, then our electronic geometry, we said that was linear. Right? If we have three electron groups, that's sp2, and we just said that that was trigonal planar. 4 electron groups, sp3. That was tetrahedral. That was our CH4 example. Could we have sp4 hybridization? It turns out we can't. We can't mix a 2s and a 2p with a 3p orbital, right? And there's only 3 2p orbitals. Remember when we talked about expanded octets, we said that only those atoms that have empty d subshells could have expanded octets. Here's where those d subshells come in. So for 5 electron groups, it turns out that we take 1s, 3 p's, and a d to make those hybrid orbitals. This would be our trigonal bipyramidal. And for 6 electron groups, we have to add in one more d orbital, and so we end up with sp3d2. And remember, that was octahedral. Notice that the number of electron groups correlates directly with the number of hybrid orbitals, right? 2 electron groups, we need 1s and 1p. 3 electron groups, 1s and 2 p's for a total of 3. 5 electron groups, an s, 3 p's, and a d. 5 orbitals, right? And so then each electron group sort of gets its own hybrid orbital when we do that hybridization process. Okay. So let's determine the hybridization state of the central atoms. The underlining didn't come through, but these are our central atoms. So beryllium hydride here. Beryllium goes in the middle. We have a hydrogen on each side. Beryllium brings 2 valence electrons. Hydrogen each bring 1. So that's a total of 4 electrons. We have 4 electrons. How many electron groups are on the central beryllium? 2. There's only 2 bonds, no lone pairs. And so there's 2 electron groups. I'm going to abbreviate that EG. So that means that it must be sp hybridized. Aluminum triiodide. I have aluminum. Aluminum brings 3. Each iodide brings 7, so that's a total of 24 electrons. We've got 6 already. 8, 10, 12, 14, 16, 18, 20, 22, 24. Aluminum is just below boron in the periodic table, so like boron, it's okay with having just 6 electrons. It turns out that because aluminum is in the position it is, that aluminum iodide bond is kind of polar, kind of ionic. It's one of those that's kind of in the middle. And so sometimes we think about it as a covalent bond like we're doing now. Sometimes we think about it as an ionic bond, especially when it comes to naming. We've been naming this aluminum iodide, not aluminum triiodide. Right? And so aluminum is okay with just 6 valence electrons. And so we have 3 electron groups. Right? So that means it must be sp2 hybridized. This last one, PF3, phosphorus has 5, 3 fluorines bring 21 total, so that's 26 electrons. There's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have 4 electron groups, 3 bonds, and a lone pair. And so we end up with sp3 hybridization. Now, I know that in the last video I did nitrate a lot as an example. I'm going to quickly draw nitrate again. He's in double bonded O. I'm not going to draw his resonance structures, but there's nitrate. Nitrate has how many electron groups? I hope you said 3. A double bond, remember, is just 1 electron group. And so he's got 3 electron groups, so he has sp2 hybridization. When we talk about the hybridization of carbon, and especially the ones where we leave some p orbitals unhybridized, what happens to those p orbitals? And so Again, we're going to start with carbon. He has an sp, he has a 2s and 2p. This is where we start with carbon. If we undergo sp2 hybridization, what we end up with is something that looks a little bit like this. These are sp2 hybridized, and we still have a 2p left over. It turns out that what happens, even though he was never hybridized, he still gets an electron. And so what happens is we end up with this extra p orbital that's not really contributing to the geometry of our molecule. So this guy doesn't contribute to the geometry. So let's think back through chapter 9 and 10. Where did we see extra electrons that don't change the geometry of our molecule? We saw those in double and triple bonds. And so what happens is these hybridized orbitals make all of our single bonds, and then these unhybridized orbitals, or orbital in this case, makes that double bond, or a triple bond, but in this case there's only one extra, so we can only make one extra bond. We call the bonds that hybridized orbitals make sigma bonds, and the orbitals that, and the bonds that unhybridized orbitals make, pi bonds. So sigma bonds and pi bonds. So let's take a look at an example. Here we have ethylene, C2H4. It turns out that these carbons in ethylene are sp2 hybridized. And so in green, we have sp2 orbitals. And those sp2 orbitals making a single bond here with this overlap, a single bond here with this overlap, a single bond here with this overlap, and a single bond here with this overlap. And in the middle, we have a single bond between the two carbons. Okay. Now, what we can't see on this image, but we can see in the middle image, is that each of those carbons has an unhybridized 2p orbital. Right? Those 2p orbitals overlap to form another bond. Right? Now, I need to be a little clear here. They do overlap both above and below the molecule. Hopefully you can tell, right, over here is an H and over here is an H, 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 right? There's our molecule in there. And so the p orbitals, just because of their shape, they overlap above and below the sigma bond. So remember, this overlap in between the two carbons, because it's the hybrid orbitals overlapping, that's a sigma bond. This is sigma. The p orbitals that overlap above and below count as one bond, because that p orbital is sort of that double balloon shape. Those orbitals overlapping happen to overlap in two regions, but it's still just one bond. And so that forms the pi bond, right? And so what we see here is this overlap forms a sigma bond between carbon and hydrogen, another sigma bond between carbon and hydrogen, another sigma bond between carbon and hydrogen, another sigma bond between carbon and hydrogen, and one sigma bond between carbon and carbon. Right? The thing that I really need you to remember is that this pi bond and this pi bond are just one pi bond. Right? Every pi bond has two regions of overlap. Every sigma bond has just one region. Every pi bond has two regions. And so when we think about a single bond, that's what we have over here between carbon and hydrogen. Right? That's just one sigma. A double bond, that's what we have between carbon and carbon over here. Well, you see we have one sigma, but we also have a pi bond. So it's one sigma and one pi. It turns out that a triple bond is one sigma and two pi. And so every single bond that you see in a structure, count that as a sigma bond. Every double bond that you see in a structure counts as one sigma and one pi. And every triple bond that you see in a structure counts as one sigma and two pi bonds. Okay? Let's look at C2H2. In this case, we have, again, overlap between the carbon and the hydrogen. That counts as a sigma bond. Overlap between the carbon and the hydrogen. That counts as a sigma bond. And in the middle here, overlap between carbon and carbon counts as a sigma bond. We have two unhybridized p orbitals. One of those is in the z dimension, and so they overlap, and we get one pi bond. One of those is in the y dimension. They overlap, and we get one pi bond. And so you can see here in purple, we have a sigma bond to hydrogen, a sigma bond to hydrogen, and in the middle, even though it's not labeled, that's a sigma bond between the two carbons. Here, I'm going to sort of change some colors around. This cloud of pi and this opposite cloud of pi form one pi bond, and then the other two that I'm going to just leave yellow, those form the second pi bond. Right? And so again, pi bonds occur above and below the sigma bond. And so the yellow ones are one pi bond, and the blue ones are another pi bond. So let's look at the bonding in the formaldehyde molecule, CH2O. We saw formaldehyde in chapter 9, so it should be familiar to you. We have C in the middle, we have an H, we have an H, we have an O. Carbon brings 4, hydrogen each brings 1, so that's 2. Oxygen brings 6, that's a total of 12 electrons. We have 6 already. Hydrogen doesn't need any more. 8, 10, 12. Used up all of our electrons. We're going to push in a lone pair to form a double bond. And this is our Lewis structure. Before we go any further, let's think for a minute what the geometry of this guy is. He's got 3 electron groups. Remember, a double bond counts as 1 electron group. So we should draw him, really, as a trigonal planar kind of molecule. So he should look more like that. 3 electron groups means 3 sigma bonds. A double bond means 1 pi bond. So 3 sigma, 1 pi. What hybridization goes along with that? Well, if we need 3 sigma bonds, then that's going to be an sp2 hybridized. Now, if I wanted to, I could ask the hybridization around oxygen as well. This oxygen has how many electron groups? Still 3. Each lone pair counts as an electron group, so does each bond. And so he's got 3 electron groups with 1 double bond, and so he's also sp2 hybridized. Right? Oxygen needs 1 hybrid orbital for his sigma bond, and 1 hybrid orbital for each lone pair, plus an unhybridized p orbital for that double bond, that pi bond. Okay. All right, excellent. That's chapter 10. Let me know if you have any questions. I know that these were a bit longer videos, but that wraps up this material and the material for the course. Take care.